Welcome to this lecture about heating and cooling demands of buildings. My name is Laure Itard. After this lecture, you will be able to make simple estimates of the heating and cooling demands of buildings. We will address space heating and cooling as well as hot tap water. You will understand the difference between energy demand, supply and distribution and be able to size equipment using the nominal power. And you will know how to use building typologies to make estimates at neighborhood or city level. In another lecture, you have discovered already that the gas use in buildings, see on the right, correlates quite well with the energy levels, see picture on the left. Higher gas consumptions are red, just like buildings with a poor energy level. These buildings are also poorly insulated, so in the inner center of Amsterdam there are many old non-insulated buildings, while at the periphery there are more recently built with a higher level of insulation. This is somehow reflected in the gas use on the right picture. When designing a city or neighborhood heating grid, you need to know what is the heating demand in the area. To estimate this heating demand at district level, we generally make use of standard building typologies. You see here an example from the Netherlands. A neighborhood may, for instance, consist of X dwellings of type TH, terraced houses built before 1964, A buildings of type AB, apartment blocks built between 75 and 92, and Z buildings of type SFH, single-family house, built between 64 and 74. If you know the heating energy demand for each of these three types, you can then easily extrapolate to the whole district. On the website of Episcope, you can find more typologies for other European countries. You are now going to learn how to estimate the space heating and cooling demand of a building. Space heating and cooling is about maintaining a nice indoor temperature, generally between 18 and 25 degrees Celsius. The space heating and cooling demand has nothing to do with the type of heating or cooling system you choose. It depends only on the construction, the weather, and the people inside and their activities. Based on this, we can estimate how much heating and cooling is needed to maintain nice indoor conditions. Once the energy demand is known, you can use this knowledge to choose and size heating and cooling equipment, like for instance a home boiler, heat pump, chiller, or a centralized geothermal or biomass plant. And once you have made this choice, you can design the distribution system, bringing heat and cold from the supply equipment to the buildings and to rooms in the building. This lecture addresses step 1, the energy demand. What are the thermal processes responsible for the energy demand for space heating and cooling? Basically, there are 4 main energy transfer processes responsible for heat flowing in and out a building. The first one consists of the energy flows through the building envelope. What we call the building envelope is in fact a construction, facade walls, floor, roof, windows. We call these flows transmission heat flows, and they arise simply because of temperature differences between indoor and outdoor. The second one is about the energy coming with air flows from outside. We call them ventilation and infiltration flows. The third one relates to the sun. When the sun shines, the building gains energy through solar radiation. The fourth and last one is about internal heat gains by people and appliances inside the building. We are going to make a balance of these 4 heat transfer processes in order to find out if the air in the building needs heat or cold to be at a nice temperature. We can make an energy balance because of the first law of thermodynamics, which is the law of conservation of energy. For the energy balance, we will be summing up all four energy amounts transferred to and out of the buildings. We have seen that it is transmission, ventilation and infiltration, solar heat gains, and internal heat gains. There are three cases. First, if the balance is zero, the system is balanced. There is as much energy flowing into the building as leaving the building, so no heating or cooling is needed. The desired indoor temperature is naturally achieved. In the frame, you see an example of such a case. Second, if the balance is negative, this means that more energy leaves the building than it comes in. There is therefore a deficit in heat, meaning that the indoor temperature will drop down to restore the balance. If you don't want this temperature decrease, you need to add as much heat as needed to bring the balance to zero. That is what we call the energy demand for heating. In this example of a cold hour, you see now such a case where heating is needed. If the balance is positive, this means that more energy comes in the building than it leaves. There is therefore a surplus of heat, leading to an increase of the indoor temperature, restoring the balance. If you don't want this temperature increase, you need to remove energy from the system. That is, you need to apply as much cooling as needed to bring the balance to zero, which is what we call the energy demand for cooling. This time we choose a warm hour in the year. Note that the cooling is negative because it is about removing heat from the building. Now that you have learned how to make an energy balance, let's look at how to calculate the different parts of the balance. Let's start with the heat transmission through the envelope. You see on the picture right a wall, but it would be exactly the same for a floor, roof or a window. The heat transferred by transmission is calculated as a function of the temperature difference between outdoor and indoor, the surface area A of the wall and the heat transfer coefficient U, which is the inverse of the heat resistance R. The heat resistance of the material itself depends on its thickness and its thermal conductivity. This slide shows some typical R values of diverse building materials and also their U value calculated like in the previous slide. Below we also show the values that should be achieved in Dutch new build according to the Dutch Building Code. Let's look now at infiltration and ventilation heat transfer. Infiltration is the air that flows in or out the building through cracks in the construction and poor ceilings. It cannot be controlled, depends on wind pressure and in general is not enough to ensure a good ventilation. Ventilation is the air that is brought on purpose into the building. To ensure a good and healthy indoor climate, a minimum of 36 cubic meter per hour per person is required. Also, when it is very cold or very warm outside, ventilation is always needed. It is essential for health. That is the reason that in buildings with lots of occupants, like a school, you see these big ducts transporting air. There are only 4 ways of ventilating a building. The first one is natural ventilation, such as opening a window or by ventilation grills. The system works only well if there is enough wind pressure difference between the different facades, which is often not the case. That is why we try to assist the ventilation by a ventilator. You can place a ventilator, a fan, to push the air out of the building. You can also use a ventilator to push the air in the building. It then creates an overpressure by which the air automatically goes out through the chimney or the window. And finally, we have the balance system, in which there are 2 ventilators, one for supply, one for exhaust. The main advantage is that heat recovery is possible, as indicated by this arrow. It saves lots of energy. To calculate the heat transfer due to ventilation and infiltration, you can use this equation. The solar heat gains now. For a quick estimation of solar gains, we consider only the windows. Here is a cross-section of a building. When the sun shines on the window, a part of the solar radiation is blocked because the window is not fully transparent to radiation and it absorbs a bit of it, which produces an increase of the window temperature. Second, the part of the radiation that is not blocked arrives in the room and goes through the air, which is transparent for solar radiation, to the indoor walls and floors in which it is absorbed. By absorbing the radiation, they become warmer and warmer. At a certain moment, the walls and floors are warmer than the indoor air and start releasing their heat to the room by convection. This introduces a delay in the amount of heat coming free in the indoor air. For quick estimations, you can use this equation in which the solar factor indicates how much solar energy is transmitted through the glass and the solar blinds. You see in the first table some typical values of solar factors of blinds, and in the second table some typical values of solar factors of different types of glazing. Last but not least, we have the internal heat gains, which are the amounts of heat generated inside a building due to the use of appliances and lighting and the presence of people. Due to their metabolism, people have a heat rate delivery of around 117 watts per person. Depending on the density of occupancy, this will cause more or less internal heat. For instance, houses are generally not densely populated, by which the rate of heat production by people is around 2 watts per square meter floor area. In an office building, it would be more around 5. Next to this, we have appliances and lighting, which both are powered by electricity. But because the law of conservation of energy, this electricity finally ends up as heat in the room. This slide shows some averages you can work with for quick estimations. If we have hourly temperature and solar radiation data, for instance from a meteorological institute, we can make very easily an energy balance per hour. And if we can make it for 1 hour, we can also make it for all 8760 hours of a complete year, like is done in most building simulation software like Energy Plus, ESPR, Transys, etc. And this is the result for one specific building where I calculated the energy balance 8760 times and summed up all of them, resulting to a total of 3646 kilowatt-hour annual heating demand and 605 kilowatt-hour yearly cooling demand. That is what you can find on your energy bill. And I also plotted the graphics with all hourly loads. Most important, you see also on the graphic the nominal heating load, also called nominal power. It is the maximum power the equipment should be able to deliver. For the heating, on the left, you see this peak at the end of the year in winter. The peak is 1.6 kilowatt that should be delivered by the heating equipment. For the cooling, on the right, you see that the maximum power is achieved in the summer and is 1.8 kilowatt that should be delivered by the cooling equipment. The price of equipment depends on this nominal load in kilowatt. The energy bills of the residents depend on the annual energy demand in kilowatt hour. Buildings also need energy to heat tap water for showering or doing the dishes. Hot tap water has a share of 15 to 25% of the total energy use. The yearly heating energy demand for hot tap water can be calculated by the equation on this slide. The blue table gives typical volumes of water used in a liter per day in US in different types of buildings. This is of course very dependent on local culture, circumstances and climate. In the Netherlands, we assume the temperature of cold water T-cold to be 10 degrees on average. A temperature T-hot of 45 to 50 degrees is enough to deliver hot water. However, many systems are continuously heated to 60 degrees to avoid the growth of Legionella. Last but not least, it becomes more common that measured heating energy data at street or district level is made available by energy companies, municipalities or the government, just like we see in the picture right. In that case, it may be very useful to use this data to check and calibrate your calculations. In some cases, you could also use only the measured data instead of the calculated ones. But as we will see in another presentation, knowledge of the thermal quality of the building is needed to make the right choices of the heating system. So you will still need to look at the typologies of the building in the neighborhood. In this lecture, you have learned how to estimate the heating and cooling needs of buildings by making a balance. You understand that the transmission heat flow can be decreased by increased insulation. You understand that reducing infiltration is right, but reducing ventilation below 36 cubic meters per hour per person should never be done for health reasons. Energy can be saved on ventilation losses by applying heat recovery. Cooling demand can be reduced by applying solar blinds or coated glass. It can also be reduced by ventilating with cold outdoor air when outdoor air is cooler than indoors. You have an idea about the energy demand of hot tap water and you understand the difference between power and energy use. Finally, at district level, you need to make estimates for the different building typologies in the district. Thank you for listening.